Hello everyone, my name is Qidong Wang. I'm a PhD student at University Paris CIDE under the supervision of Professor Samis Kapnas. Today I'm going to share with you our work IDEAL, which is a deep learning framework that detects highly imbalanced interictal epiform discharges. It is collaborated with neuroscientists from Paris Pre Institute, Stephen Whitmarsh and Vincent Navarro. So our problem is to detect the interictal epiform discharges, which we call them IED. So on the left side of the figures, so we are showing an example of the IED pattern in the EEG dataset. So basically we are detecting IED from the EEG, multi-channel EEG series. And it is recorded as we show on the right side of the figure. So basically we insert an electrode into the brain of the patient, and each electrode has multi-contact, and each contact will collect the signal for each channel of the data we saw on the left side. So basically, IED patterns, they are actually very useful to detect for the analysis and diagnosis of the epilepsy. Epilepsy is the second most worrisome neurology disorders worldwide. And also usually what EEG data is what is used to diagnose the epilepsy. So IED patterns, actually, they are short morphology-defined events in the EEG series. By morphology-defined, which means morphology-defined means that there is no formal definition using the amplifier or the length of the signals. So they are mostly based on their identification was mostly based on the experience of the clinicians. And actually, the detection of IED can be very it can help to diagnosis and study of the epilepsy. And moreover, that if we can successfully detect the IED patterns, it can help to facilitate the identification of the brain areas in which the seizures was initiated. This can be served as a further indication for the clinicians to conduct some surgery or treatment. However, although it is very useful, it is very time consuming. So actually, manually annotate the EEG patterns, even for single patient and for single day recording. It actually can take one neuroscientist up to 2 weeks. Actually, this motivates us to develop accurate and automatic detection method for the IED patterns. So the detection of IED patterns, the problem of IED detection is actually actively studied in the field of neuroscience, but it is not as much as it has been studied in computer science. So basically, the works can be divided into two categories. So the first category is based on the template-based detection method. So in the left side, in the figure in the left side, I'm showing like the templates for a set of patients. So each row corresponds to a patient, and each column corresponds to one template for this patient. So basically, this is the template bank for a set of patients. And then the templates are searched over the whole series to identify some IED patterns. And on the right side, so there are some deep learning-based methods. So this deep learning-based method has also been found successful in the detection of IEDs. So this figure demonstrates one state-of-the-art method in the neuroscience community. It is first using sliding window to segment the series into some sequences and then transfer each subsequence into a spectrogram. And then they run a 2D ResNet-18 to detect the IED patterns based on the spectrograms. However, both of these methods are some problems. For the templates-based method, actually, it requires very heavy manually tuning of the templates. For example, they should be aligned in the time domain. And both you can see that there is a peak and also a slow wave. So both the peak and slow wave should be carefully aligned to facilitate the effective detection of the IED patterns. For the deep learning-based method, this kind of method that has been developed for the neuroscience community, actually they're mostly based on the spectrogram. So actually, if the calculation of the spectrogram is actually very heavy. Second, so actually, as we will show later, this training and inference of the method, actually, they are ignorance of the imbalanced nature of the IED patterns. So why does imbalance matters here? So for example, by imbalance, we mean that there is only a few IED patterns in the dataset. The majority of the patterns in the dataset, they are just non-IEDs. Non-IED means that they are either some normal behaviors or they are some random noises. And imbalance property is actually a very bi-natural characteristic for the IED patterns across all the patients. For example, here, these are the patients, these are the dataset we have evaluated in our experiments. So some of them are from France, from the Paris Brain Institute, and some of them are from the US, from the Temple University Hospital. We can see there the P1 is an imbalance ratio, which means it is the number of IED pen examples divided by the whole number of examples. This can be as low as 1%. So this means this indicates generally that this set is extremely imbalanced. But why this matters to us? So actually, this is coming from the fact that most of the neural network is by default training towards accuracy. Accuracy basically means that it wants to accurately predict every example in the dataset. So this has naturally prone to correctly predict the majority class, which are the non-IEDs. So in this method, actually we propose a new loss function, which we call them SASU. SASU is coming from sampling-based surrogate loss function to rectify the impact of imbalance. So basically, SASU is a surrogate F beta loss function. So F beta is the harmonic average of prediction recall for the IED patterns. So basically, by optimizing towards F beta score, actually we are putting more focus on the IED examples rather than the non-IED examples. So this is just a full picture of our framework, which we call it IDEAL. So first, IDEAL detects the IED patterns on the raw series. So this can enable fast inference compared with some other state-of-the-art neuroscience methods that are working on the spectral diagrams. And second, it actually handles the imbalance explicitly by deploying the new surrogate loss function. And also in this new surrogate loss function, we further employed a sampling-based method to further adjust the descent boundaries. So by doing so, we can enable the accurate IED detection based on the IED framework. So we will quickly go through the elements in this framework. So first, there's our detection model is an exponentially dilated residual convolutional network. Actually, it's coming from the CNET. CNET is a network that is trained on very large dataset for learning a distance matrix or time series. And our loss function, as we show here, so it has a little bit complex formula. We will not go into the details, but rather just introduce you some intuitions, some design intuitions of this formula. So first, we actually have the beta term in this formula. And beta, as in F beta, is actually the term that balances the prediction recall. And as we know that in neuroscience, false alarm rate is important. And prediction here actually equals to 1 minus false alarm rate. So basically by introducing F beta score in this equation, we can enable the tuning of false alarm rate based on the demand of the neuroscientists. And also we have this term in the front of each part, so that are used to smoothen the gradients. Basically, these are inspired by the focal loss. So the idea is that if the model makes more accurate prediction for each different classes, so their gradients are further spread to close to 0. The third term here is actually the imbalance ratio, basically, as we mentioned. So this is actually the number of IED examples divided by the number of non-IED examples. And here, alpha is actually the sampling ratio of the non-IED examples. So basically, this term can be automatically collected from the statistics of the dataset, and it can also be inputted by the neuroscientist. So if it is inputted by enabling it, it can be inputted by the neuroscientist. Basically, we want to facilitate the neuroscientist that they can tune these deep learning models based on zero domain knowledge. For example, they can infer the frequency of the IED patterns based on the clinical observations of the patient. So to wrap up, by combining the raw series-based architecture and also the new surrogate loss function, we can enable fast inference because we are actually detecting directly on the raw series. And also our detection is also accurate because we can tune we train our network towards the F-beta score, and also it is further adjusted by sampling the non-IED examples. So we run our experiments on 11 real-world datasets. So some of them are from the Paris-Bree Institute, and some of them are from the Temple University Hospital. And the imbalance ratio, the number of IED examples divided by all the examples vary from 1% to 21%. So first, we evaluate the accuracy of the model using the F-band score. We compare the result of IDEAL to both some results in the IED detection method in neuroscience and also some other method of time series classification in the recent time series classification method. So we show that actually IDEAL achieved the highest F-band score. And further, we evaluate the inference time of the IED framework. So basically, you can see that benefited from just inferencing on the raw series. Actually, our method is 100 times faster than the existing method based on neuroscience, based on the neuroscience method, based on the spectrograms. So to wrap up, so by these results, actually, we can safely conclude that IDEAL actually enables annotations of weeks of data, which was not possible before for the neuroscientists. So this actually enables much more study opportunities for neuroscientists. And further, to facilitate the study of neuroscientists, actually we implement IDEAL in a software like we show here. So basically in this software, the neuroscientists can upload their dataset, can zoom in, zoom out to check the details of each channel or each time frame. And also they can select the model and train it and then check the predictions on the bottom line. And also they can explore some like pre-processing steps for each dataset. And furthermore, as we have been mentioned before, so we have introduced the imbalance ratio as an explicit tuning knob for neuroscientists to fine-tune the model based on their domain knowledge. So to conclude our work, so basically in this paper, we propose IDEAL framework to efficiently detect the IED patterns. So it is fast because it runs directly on the real-time series, and also it is accurate because we actually use a new surrogate loss function to put more force on the IED example. And also the decision boundary is further adjusted by sampling the majority class, which is the non-IED patterns. And we implement our IED algorithm in a software, so which we show a little bit demo. And actually that can further facilitate the usage of the neuroscientist. So some future works could be like how can we more wisely transfer the knowledge of the model between different patients, because it can be quite different, because different IEDs between different patients can be quite different. And also second is that we want to, based on our software, we want to explore more neuroscience applications. For example, whether we can detect some other complex patterns like the benign sporadic sleep spikes or some like decade spikes. So thank you very much for your attention. That's all for my presentation. And if you're interested in our work, you can just feel free to scan the QR code or check the link for some online resources, including the code, the data, and some other materials. Thank you.